So let's get started with this rate law mechanism intro worksheet. And my purpose here is trying to teach you something about mechanisms, which are individual steps that represent an overall reaction. Most reactions are represented by these mechanisms. We just don't think about it because we tend to look at an overall reaction like the one written here as, hey, that must be a single step because it's written that way. But most reactions are not single steps. Single step reactions are called elementary steps. And what we do in rate law with mechanisms, we're able to figure out the equation, the rate law, from the mechanism that best supports the rate law that we get from experimental evidence. So what we have here in this worksheet, two proposed mechanisms. We'll call this mechanism A and mechanism B. And what we can do here is say these are two proposed mechanisms that a group of scientists are trying to find out which one represents that overall reaction the best. And one of the ways to verify that the mechanism does support that reaction is if you look at the individual steps, can you cancel out all the catalysts or intermediates in between and get the overall reaction? So if I look at the A reaction, we should be able to see that, whoa, there is this oxygen here that is released in step 1 but absorbed in step 2. And so essentially that's going to be canceled. And what you're going to get is 2NO plus the O2 molecule is going to give you 2 NO2s, which is exactly the reaction that we have above. So far, just by canceling out what we call these intermediates or possibly catalysts, and I'll talk about them in a second, this does support this so far. If I look at mechanism 2, I can see the same thing. I see another chemical that's not in the overall reaction written above that I can cancel out. And of course, checking to see that I get 2NO plus an oxygen gives me 2NO2. And it does. So both of these mechanisms support so far that they are representative of this overall reaction written here. Now, we need more data here because we need to know if in fact they actually are supported by something called the rate law. The rate law, as you've been learning, is a formula that means the rate, which usually means the molarity per second of the product you're producing, so the speed at which there's the appearance of the product. Remember, rate law is a measure of a path function. In this case, how fast the reaction occurs is equal to a rate law constant, which, by the way, is a proportionality constant, which is sensitive to temperature and activation energy. And then you're going to times that by the initial concentrations of the reactants. In this case, we have NO, and then we have O2. So these brackets means molarity, and these are the initial concentrations. And it should make sense, okay? If the concentrations of our reactants are high, hey, they're going to collide with each other at a greater frequency, and that's going to lead to more effective collisions and reactions. Don't forget, for a chemical reaction to go, there must be a physical collision. So one of the factors of how fast a reaction goes, that's the pathway, is what's the frequency of collisions. And so by increasing the concentration, we increase those frequency of collisions, and there's going to be more successful collisions called effective collisions that lead to the products. Okay, so I'm going to get rid of those arrows again. So that's the basic formula. Now what I left out though is the order here. What are these orders that we call? Okay, how does changing one of these element, or in this case molecules, affect the rate? Well, we need an experiment to do that. Well, now we're going to get to that experiment first in a second, but let's take a closer look at what we canceled out in the mechanism. Okay, now getting back to the mechanism. All right, I kind of want to cancel. Look at what we did over here with the oxygen here. Okay, this oxygen is called an intermediate. Okay, I want to put a little box around it. and it's an intermediate. It's that important. I'm going to write the word intermediate. Intermediates are made, okay, by usually the step occurring in front of the next step. If you want to talk about this for a second. So intermediates are made by one of the steps, and it connects one step to the other. In this case, we only have two steps. So we can see that NO and O2 come together to make oxygen. Now, an oxygen atom. Oxygen exists as O2, so it's a free atom. We call it a free radical. That is a very highly, extremely reactive chemical species. It's not going to stick around. And so it's going to quickly react with the NO to make NO2. So you should recognize that any intermediate, to identify an intermediate, you must understand that it links one step to the next step. Okay, so we produce the oxygen here, and we use that oxygen for the second step. So the second step's kind of waiting on the first step. Now, the second step, my friends, has to be the fast step. And the reason why it's fast is because intermediates are highly reactive, and it kind of makes sense. We're trying to, thermodynamically, or if you think about it, to go to a next step. Now, there's only two in these, but these steps could have multiple steps. So if you're going from the first step to the third step to the fourth step, if there's more than them, it should make sense. The driving factor is the instability, okay, of the intermediates. So we should recognize that when they're made, they're unstable, and they're going to drive this process forward to the completion of all the steps. In any case, this must be the slow step. The second step's waiting for this highly reactive component to be made, and then as soon as it's made, boom, this second step is fast. So again, intermediates link steps from one to the other, and of course they also drive them because of their instability, meaning they're going to react quickly. If you look at step one, we produce another intermediate, N2O2, and you notice that reacts with O2 to make what we need is the products here. And you notice the intermediates, as I did not mention, are not in the overall reaction because they're canceled off. They're produced and then they're used up. And of course, what they're doing is they're linking one step to the other. All right? And again, they're highly reactive, and it makes sense that they're highly reactive because it drives the process forward. Now, we don't have any catalysts. I'd like to mention that. If we had a catalyst, we'd have something on the reactant side. Let's just put like C here. And with the catalyst, it would be reproduced at the end. If you notice, catalysts don't get consumed. You put them in and they get reproduced. And we'll talk about them a little bit later. Catalysts actually create these different pathways, and we'll talk more about that. But in any case, we've established here that the fast steps are going to be the second step because we're producing an intermediate in the first step of both of these mechanisms. And the slow step is step one in both of them. Now, the slowest step is something called the rate determining step. So the rate determining step is the slowest step. So step one for both of these is the rate determining step because we have two steps, a slow step and a fast step. The entire process, guess what, is based upon the slowest step. Ever think about a team? You're only as good as your weakest link. Well, the weakest link here is the slowest step. So we're only as fast in producing the overall reaction, but by these two individual steps in each mechanism as our slowest step. So the entire rate is determined by that. So we can actually write a rate law based upon the elementary steps in the mechanism. And so let's go ahead and do that. All right. So the rate law for A would be R equals K, the concentration of NO times the concentration. These are initial concentrations. And when I look at this first step, okay, I can see that there is a coefficient of 1 here and 1 here. And that would mean that the orders are 1. And careful here, the orders equal the coefficients only if you have a single step. The only time you know you have a single step if the problem tells you that or you're taking it out of a mechanism. Other than that, we need experimental evidence. And the reason why it works is kind of cool. So if I double the amount of NO in this reaction vessel and keep O2 constant, it should make sense that NO is going to hit and collide with O2 twice as frequent. And that means what we do to the NO, we're going to do to the rate. So if we double the NO, NO is going to hit O2 twice as much. And we would say that NO goes up, okay, in concentration. It's also going to go up with the rate law. Whatever we do to NO, we do to the rate law if we keep what? O2 constant. And that's a first order concept. So that should make sense. And for the same reasoning, if I was to double O2 and keep NO constant, hey, what's going to happen there is I'm going to hit, or O2 is going to hit NO twice as much. And therefore the rate's going to go twice as high. If I add 3 times as much O2, I'm going to increase the rate 3 times as much. Whatever I do to O2, guess what? The rate is going to do the same, and it's called first order. And that's why having a one-to-one relationship creates that scenario, if you can follow. In any case, if you don't, it's just easy to understand very simply that if you have a single step and you only have that in a mechanism, the coefficients are the orders. Okay, so moving on, okay, to the other rate, okay, and again, same idea, R is equal to K, it's a rate law constant, and it'll be NO, all right, and same O2, and by the way, I'm just starting with the reactants of the overall, and in this case, the rate determining step, all right, for step 1 here, I only have 2 NOs. So, my friends, that would mean I have a coefficient of 2 and I have an order of 2. Stop right there. If I have an order of 2 from a coefficient of 2, it's only because this is a single step process. And if you think with me for a second, if I double NO and both are NO, then I'm going to quadruple the number of collisions here. Okay, if you can think with that. And quadrupling when you double is the square of the change. The square of 2 is 4. And that's how we come up with a second order there. Now, this is the most important part thing I think is here, is that if you notice in the slow step, there is no oxygen. Where is the oxygen in the first step? It's not there. So that would mean that the oxygen, the amount of oxygen, has no effect on this rate. You have to have it for the reaction to work, but it's not there, so we get a 0 order, and you should recognize something. Anytime anything goes to 0, that goes to 1. So these have markedly different rate laws. We don't know which one is right, so we're going to need some experimental evidence, and here it is. Okay, let's determine the rate law from the experimental evidence. Now I'm going to use the eyeball method, okay, to do this. Okay, and I say eyeball method because these numbers are very nice and tidy. So let's do this. Let's use experiment 1 and 2, and I'm going to keep the NO constant. It's my control there, and I'm going to double, okay, times 2 the O2. And what happens to my rate? The rate doesn't change. So doubling the O2 has, no rate. So right away, when I write my rate law, R equals K, and again, it's just the reactants of the overall, and I get O2 have to have 0 order. It has no effect. You already can see which rate law is being supported here. It looks like the second one I have up here is being supported because we have a 0 here, but that's what it means. Okay, let's see if we get a second order for the NO. All right, well, I'm going to go from 3 to 2 here, and I'm using this one because I like getting bigger. You could do this getting smaller, but I kind of work, my brain works that way. So if I double NO and I keep O2 constant, what happens to my rate? Oh, look at that. From 2 to 8, you can see that's going up 4 times. This is doubling. Now think with me for a second. The rate, of course, it equals some constant. If we're just looking at NO, well, if NO is doubling, but the rate is what? Becoming 4 times as great, it must mean there must be a square here. So when you think about the rate is the square of the change of the NO. That's what it means. The rate, in this case, is the square of the change of NO concentration. And that's how I get a second order. And there's a couple different ways you can get a second order. Like if, for instance, and this is not the case in this case, but so I said case twice, kind of weird. But if I was to increase this 4 times, if it was second order, how much would this have to increase? 16. Yeah, you did that right. You know, and you don't have to have second orders too. You can have an order of 3, right? So if this increased 3 times, and this was actually a 3 here, okay, then this would increase, you got it, 27 times, because 3 cubed is 27, okay? So that's not the case, but I'm just showing you how you can have those other orders, okay? So that's what we're doing there. All right, so in any case, we've got from the experimental evidence, what do we have? Well, we have our rate law and our orders, and it's clear that the winning proposed mechanism for 2 reasons. Number one, it was able to what? I was able to cancel out the intermediates and or catalysts that we had, and we didn't, and get the overall reaction from all the steps. And does the slow rate determining step support the mechanism? And it does. And the mechanism we get from experimental evidence is supported by this value, this rate law that we get from the mechanism. Okay, a couple other skills we'll do is let's calculate the rate law constant as a nice review here. So let's get back on our rate law horse, okay? And so we've got our rate law, and if it's a constant, we should know that the rate law constant is going to stay constant. It does change with temperature, but again, we're just going to write this formula that we now know. By the way, I'm not going to write the O2 because O2 to the first power is 1, so this is really my rate law. You can write them both ways, but I'm going to keep it that way. So I'm going to pick experiment 1. I could pick any experiment I want because the rate law stays constant, but I'm going to put in the NO here. It's 0.08, and it's squared because we found that as the second order. The K is what we're solving for, and what is the rate? The rate is 8 times 10 to the negative 5. Notice the unit here is molarity per second. Negative 1 means per second. So algebraically, I'm going to solve for K. So the K is equal to 8 times 10 to the negative 5 over 0.08 squared. We're going to put that into our handy-dandy calculator, okay? And so we get the 8 to the negative 5, divide by the parentheses, because I got to square that first, 0.08 squared. Close that parentheses, and I get my K to equal, my rate law constant, 0.0125. Now, anytime they ever ask for the value of the rate law constant, they want the units, whether they say it or not. So we've got usually 1 point on the AP for the K, but you're going to get what? You're going to get more points if you give me the units. Now, what would the units be? Well, we put the units in here and solve for K again. This is a rate, and up here we have molarity second, so it's a molarity per second. Second to the negative 1 just means on the denominator, all over, okay, ooh, look at that, molarity squared, okay, so I'll just rewrite this over here. So K is equal to the molarity per second, all over molarity squared, and we should be able to see that we're going to get rid of the molarity. This goes to 1, and I'm left with 1 over second over molarity, And that's the same thing as saying 1 over molarity second. That could be the way you write it. Or you could say molarity to the negative 1 or second to the negative 1. It's the same thing. So there is, oh, Christmas. You don't want to do that. There is your units there. Okay, so they give you definitely a point for the right number and, of course, the right units. All right, and we've already determined the best mechanism, and we already talked about the 2 reasons why. I hope that helped. See you next time.